Hey, welcome to this lecture. This is actually the start of chapter 2, so I should probably little scribble up the top. So this is chapter 2, and this is atomic theory. So I would say that if the nuclear weapons are inbound and we are all going to be fried here in the next 7 minutes, then we should probably jot this down on a sheet of paper and squirrel away in a cave somewhere, because this will probably help us restart civilization as quickly as possible. So it took us thousands of years to come up with these ideas. So the Greeks came up with them thousands of years ago, and actually it wasn't until about 200 years ago we actually sort of rediscovered these ideas and saw how they were starting to make sense of things we were seeing in chemistry. So atomic theory, the basic idea is that all of matter, we said earlier, is stuff that has mass and volume, is all made up of atoms. So these teeny tiny, itty bitty little balls, somewhere on the order about 1/10 of a nanometer across. And the thing about elements is that atoms of one element, so atoms of one element, are different than atoms of another element. So they are different, so DIFF''T, to atoms of another element. And that seems kind of obvious to us, but it really wasn't obvious a couple of hundred years ago. In fact, this was sort of a amazing discovery that sort of explained a lot of stuff. A lot of people thought it was just kind of like bricks, and if you had gold, the bricks were arranged a little bit differently than if you had lead. Kind of like how your houses can look different, even though they're all built from the same building unit that is a brick. So it turns out that atoms of gold are very different than atoms of lead. So if I go ahead and use the element symbols there, AU for gold and PB for lead, we can literally draw little pictures there, and they're not labeled. If you zoom in on them, they're not labeled at all like that. But we can pretend that the atoms of gold in a lump of gold they're all the same, but they're different than the atoms of lead in a lump of lead. So these atoms of different elements are somehow different. And how does this help us understand compounds? So we said earlier, compounds can be broken down into two or more elements, always in a fixed ratio. And that's really the clue to atomic theory. Why is it always a fixed ratio? Why is salt always broken down, 100 grams of salt into 60 of chlorine and 40 of sodium? And the answer is that compounds consists of atoms in simple whole number ratios. So you've got atoms in simple whole number ratios. And that's why when you analyze a compound, it always has a fixed ratio. So why does this have to be? Well, if you've got something like water, then you've got two hydrogens and one oxygen joined together. So this is a water molecule. This is a compound. If you have something like peroxide, peroxide is made up of two atoms of hydrogen to every two atoms of oxygen, something like that. And it's got to be a fixed number ratio, right? So you can't have 2.3 children, right? You can have 1 or 2 or 3 or 0, right? But you can't have a fractional number. You can't split them. You can't split these atoms, so they have to come in fixed ratios, right? So 2 to 1, or 2 to 2, right? Or 3 to 1, right? You can't have 2.8 to 1.72. That's simply not allowed. So what makes a compound is that it's built from these atoms, and they have to be just kind of like Lego blocks. They have to be in fixed ratios. Now, one of the reasons we're a big fan of the hands-on wet course, right, the wet chemistry lab, is that you get to see chemical reactions. I'm going to write reactions as RxNS, and reactions can be explosions, right? They can be flames, they can be precipitates where you make a solid or a gel, or bubbles of gas, or they get hot, they get cold, and they look very, very impressive. But it turns out, according to atomic theory, chemical reactions are really just sort of the shuffling of atoms. So all you're really doing is changing the way the atoms are joined up. So if you light a Bunsen burner in the lab and you have a flame, what you're doing is you're taking molecules of methane and you're taking molecules of oxygen, and you are taking them and recombining them, and you're taking the carbon and methane and you are joining it up now with oxygen atoms, and you're taking the hydrogen and methane and you're joining it up with oxygen atoms. So all you're really doing, right, is just shuffling around those atoms. So if you look at that carbon there, now it ends up there. Those 4 hydrogens end up here, 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 and here. These 4 oxygens end up here, 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 and here. So you've taken methane and oxygen and converted it to carbon dioxide and a couple of waters. And that flame, right, that you see in the lab, or which you will see in the lab when you do it, right, so that blue flame right there, what it is coming through this pipe is this molecule here, methane, and sneaking through those little holes there is this oxygen. And when they combine together in this region here, they are essentially forming carbon dioxide and water. Actually, inside the flame itself, these are basically just sort of atoms that haven't quite combined yet. But once they cool down in this region up here and out here, then they form these products here. So this flame is essentially, you're seeing the hot atoms that are combining to make the products together. So that's all a chemical reaction is. When you eat a Big Mac, and you chew on it, and you break it down into smaller particles, and they go into your stomach and then your intestines, and then they're absorbed. You're essentially taking the atoms in this Big Mac, this delicious, yummy Big Mac, and you are splitting them apart from the Big Mac, and you're recombining them in your body to grow fingernails and toes and hair and eyes, or a big fat belly, or whatever it may be. So essentially all these chemical reactions are doing are just taking these atoms and they're recombining them. They're joining them up like different Lego blocks in a different fashion to make a different molecule.